All right, welcome back to stats class. So today, just like last time, there isn't a lot of stuff here. There's a lot of thinking here, okay? So this may go a little quickly. I wouldn't say quickly. We may be done before the end. That's going to happen a lot. There's going to be other days when we're not. This stuff can be very dense, and I like to give you time to process it, frankly. Okay. So we're going to talk about probability mass functions. Let's just use that. Mass functions. So that's slow, isn't it? You can plot the probability of any given score for a variable. So remember, a variable is just some thing that can take a bunch of different values. It's a number that can take different values, right? So obviously we can take a lot of different values, and we can find the probability, perhaps, of getting a given score. Now, the probability of all the events added together is 1. Right? So all the events together, all the possible events. Think about flipping a coin. The probability of getting a head is 0.5. The probability of getting a tail is 0.5. The probability of getting a tail or a head is 1. That's all you can get. Save me it's going to land on its side one time. Okay? So the probability of all events equals 1. So we know something, without even knowing anything about any of the individual events, we know that if we add all the possible events up to their probabilities, we will get 1. It will always work like that, for the universe works like this. This is just how things work. This isn't about why. It's like saying y is 2 and 2, 4. It just is, okay? So the probability of all possible events is 1. We can use that to our advantage, and we're about to. So if we were to make a curve, draw a graph of all the possible probabilities of different scores for a variable, we could then look underneath the curve, and the area under that curve should be 1. And it will. Because those are probabilities. Think about it again. We're going to have, let's say we have 2 bars. We have one that goes to 0.5 for heads, one that goes to 0.5 for tails. Oh, it's 1. The area under the curve is going to always be 1. If it's a probability, what's called a probability mass function, which is sometimes called a probability density function, which is confusing. But that's got all the scores and their possible probabilities that are put together. If we have a curve, and we have a continuous variable, so we have a curve, underneath it we have the shape of that thing, it's the area of it's going to be 1. That's obviously going to be important too. For the calculus, people who are here have taken calculus, how do you find the area under the curve? You take the integral. Okay. Are all the calculus people not here? Is that what happened?
I'm not.
So, who here is taking calculus?
Me too.
Okay, so you guys should have said curve here. Okay. Area under the curve is 1. Oh, sorry, you should have said integral. So anyway, it doesn't matter. The point is, there is a way to do this. I'm not going to teach you how to do integral calculus today. I don't think I have the time, and I don't know if I have the skills to do that. But that was just a hint telling you this is cool, and there's going to be a way that we're going to be able to do this. We're going to be able to figure this out. I'm going to show you an example of a die roll. It's a little easier. So these are, this is one of a 6-sided die, so this is a regular die, not one of the trick dies that Arwen carries around. And you realize that any die jokes is doing right to you for the rest of the term. So 0.16, right? 1 and 6 for each of those. If you take 0.16 and times it by 6, you get 1. Oh, the area under if you added all those up is 1. It's beautiful. Now, this is a weird thing, because this is the discrete variable. Discrete variables have individual possible values. We think about curves, we tend to think of continuous variables, but I think this demonstrates the idea here because, you know, it's a 6 plus 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 a 6. That's 1. Right? That just is 1. So all the possible events is 1. You could say, what is the probability? With something like this, you could actually say, what's the probability of getting a 1 or a 2? Well, we could just take a look and go 0.16 plus 0.16, the area, 0.16, it's 0.1, that's 0.33. It's 0.16. It's very cool. There's a cool kind of math, calculus, that allows you to do this without just looking at a graph and trying to figure it out. And that's what's going to be the basis of all this, but you don't have to know about the calculus. But I want you to respect calculus, is what I'm saying. So let's talk about, I've been talking about curves and probabilities and distributions. Let's talk about our favorite distribution, the normal distribution. I think we all have a favorite distribution. No, that's ridiculous. Here we go. That's the normal distribution. There's the mean, and then 1 standard deviation, 2 standard deviations, etc. All right, I think I'll put that over there. The most common, well, the one we hear about the most anyway. And it's clearly the most useful for us. This hole in the wall here, every time I see it, I think, I should just get some poly for it and fix that. It drives me crazy. I don't know why it bothers me. It does. So what are some characteristics of this distribution? It's unimodal. Look, there's only one mode. It's got one peak. Unimodal. It's symmetrical. It's a beautiful curve. It's symmetrical. And it is bell-shaped. In fact, so much so that people often call this curve a bell curve. Right. So it's bell-shaped. This curve, the function of it and its properties were discovered by a kid who was pretty bright. Baron, Gauss. You know the Gaussian distribution? It's often called the Gaussian distribution. He figured this out when he was a kid because he was really smart. Well, the rest of us were all just wrecking stuff and throwing things and playing. He was figuring this out. It's probably more fun to wreck stuff. I said the other day that if we're going to know about a batch of numbers, about a distribution, we're going to know that we have to know the shape, we have to know the central tendency, and we have to know how spread out it is. And we're getting that here. So this is good. We're going to know more about the normal distribution. So far, so good, right? Everybody's okay? Stuff you've run into before, nothing scary. Okay. You might be asking yourself, why is this useful? You might be asking me, Dave, why is this useful? And the reason it's useful to me is because it gives me a job. Pays my bills. Many variables are assumed to be normal in the population. Note the word assumed there. A lot of times they aren't. Statistics books, intro stats books are great at assuming things are normal and telling you they're normal that aren't. Right? You have a little, practice problems or maybe you get homework problems, and it'll say something like, assume that the lifespan of a light bulb is normally distributed. No, I will not. They can't be. If they were normally distributed, just as many would last for a bunch of years as would blow up as soon as you plug them in. Would you want that? No. Light bulbs are not normally distributed, and now we just assume they are for stats problems, because we run out of ideas. There are things, though, that probably are normally distributed. Human height among adults is normally distributed. Human weight among adults is normally distributed. You got to always say among adults, because if you throw kids in the mix, it screws up everything. They're all short, right? But height and weight, human IQ is, you might say, yeah, but there's a problem there. The tests are designed to make a normal distribution. Yeah, it's still fine. It still is normally distributed. So there are a lot of things in nature that are normally distributed, but it isn't a prerequisite for something, not all natural variables or variables in the world are normal. Lots of them are. The cool thing, though, is that there are kinds of distributions that are always normal, and we're going to use that to our advantage. Kinds of distributions that always come out normal. So, because a lot of variables are like this, we can say, well, let's use a whole bunch of techniques that deal with the normal distribution. There's standard techniques that have been developed over the last 150 years that have allowed us to basically do inferential statistics. So, and they work under the assumption that we're dealing with normal distributions. Or those statistical procedures are built on things that care about normal distributions. So sampling distributions are normal. What is a sampling distribution? A sampling distribution is a distribution of all the values a statistic can take. Okay? So, and I'll just put this up and then I'll explain what that means. So if we were to take the sampling distribution of the mean, well, what that is all the values the mean can take and how likely they are, okay? How many people we have here? 2, 4, 6, 7, 8, 10, 12 people. That's not enough to do my little experiment. So instead we're going to make it about the whole university and we're going to do a thought experiment instead of an actual experiment. Okay, so let's pretend we're gonna randomly select 9 people from the student body and we're going to get their height. We're just going to measure their height with a tape measure, okay? 9 people. I did that for a reason. It's going to make the math easy. Okay, so I used 9 people. So, and let's say we come out with an average the first time of, I don't know, 143 centimeters. Got a lot of short people. And then we do it again. And we sample again. 9 more people. Put everybody back in the sample, and we sample 9 more. And we get 168. And then we get 174. And then we get 183. And then one time we get a lot of guys, the men's basketball team, we get 195. And then we get 172. And then we get 178. And then we get 174. And then we get 163. All kinds of numbers. But they're all right clustered around the actual average height of Algoma University students. And let's pretend that, I think I said the other day, is 175 centimeters, so we're going to use that now as a standard. We're going to say that that's the average height of Algoma University students. I don't know if it is, we're going to pretend. So when we draw up a distribution of all the values the mean can take, or all the values that we generated, because we did all these samples of 9 people, we would get, on average, a value of 9. 9 of 175. 9 is the standard deviation. Let me put one of these up so I can draw you a bit of a picture. Does that go up? There we go. Okay. Go a little slower, don't you think? Okay. So what's going to happen is what we'd be plotting here. Okay. You can all see that. The things in everybody's way. Like I just want to make. I know it's hard for people. I don't have no idea how any of you people see. No, literally, we have no common ground here. That's why I ask to see this. Okay, so these are all this is just the probability of getting a given score, and this is the score, x. Now, in our case, x is height in centimeters, but it can be anything. I said that in the population, that the mean was 175. I don't know that it really is. I'm just pretending. What we're going to get when we get means, because these are all means of batches of numbers. We get a sample of 9, we collect 9 total, and then we get the mean, and then we plot it. And then we get another 9, and we plot it. Another 9, we plot another mean. So what we're plotting are means. You're thinking, Dave, why are we plotting means? That's weird. The numbers don't know that. You can do anything you want to numbers. There's no laws, there's no rules. You can be mean to numbers. We're going to get something like that. And in fact, this is what this says. That n says it's going to be normal. So it's normally distributed. So the sampling distribution of the mean, then, is normally distributed with a mean of mu sub x. Well, mu sub x is 175. And that's what we got. And a variance, or well, standard deviation, of sigma divided by root n. Now, I don't know what sigma would be. What would the standard deviation? 15 centimeters? How's that? That seem reasonable? I think it's reasonable. Also makes the math I'm about to do pretty easy. So we're going to say the standard deviation in the population of height of Algoma University students is 15 centimeters. This is telling us that the sampling distribution of the mean will have a variance, a standard deviation. I'm sorry. It looks like so. I just draw that out. It will be 15 over the square root of n. And I said we had 9 people. So that means it's 15 over 3. G is 5. That's why I picked 9, because I just wanted to be able to do the square root quickly in my head. It was a whole number. Okay. That's why it's useful. Yeah, it's fine if things are normally distributed, but really the key thing is the fact that sampling distributions are normally distributed. Now you might say, Dave, how the hell is that possible? That it's always like that. Well, we'll come back to it. But trust me, you will always get it such that the mean of the sampling distribution is the mean of the variable, and the standard deviation is sigma divided by the square root of that. It always shall be that way. Okay. All right. So let's look at, this is a distribution. This is a weird one. This is not the normal distribution. This is some weird triangle distribution I invented.
Oh, it's not stopped.
Well, let's do that. Not my problem. I turned the switch the other way. I mean, shouldn't that be what you do? So, if we were to find, if we wanted to know how likely we would get a score between 3 and 7, well, it's the area between those. Let's see if we can get that up a little bit. Okay. It's going to be the area here. Okay. This area. Okay. Now, that wouldn't be that hard to do. Right? Because it's a rectangle and a triangle. So we could do that. We all know these. How do you get the area of a rectangle? It's length times width. How do you get the area of a triangle? It's half base times height, right? Remember that stuff? So I see some of you going, oh, right. A long time ago, sure. But you can do that. But the problem is variables aren't distributed like houses like that. They don't get those shapes. But this, I think, gives us an idea of, this would give us the probability, because the area under the whole curve is 1. The area under here would just tell us the probability of getting a score between 3 and 7. So if we're doing the area under a curve, it's easy if you know the geometry, but most distributions aren't beautiful geometric shapes that are easy to take care of. Again, as I just said, a lot of times they're the normal distribution, right? So again, if you have, I sort of spoiled this before by saying that, calculus has a way to do this. There is math that'll let you do this. You don't have to worry about the techniques and how to do them, but there is math to do this. So, and that's some flashbacks in the back of the room. So what I'm doing here, this is just notation. I'm never going to ask you calculus notation. But what this says is, what's the area under the curve between 3 and 7? It's the integral of the function between 3 and 7. That's what that's this. Okay? That's all that means. So if there's some kind of mathematical notation, it's a pretty good guess that there is some kind of math that can do this. And there is. Again, you don't have to worry how it does it, but trust that it works. Okay? It's a real shame that, do they not teach calculus in high school anymore? I'm sorry.
It's not a requirement.
Yeah, it's optional.
It's optional.
Yeah.
But people don't take that option?
Somebody tricked me into thinking trigonometry was going to be easier than calculus.
Different than calculus. But you can do, calculus is cooler, and it's fundamental math about the universe. It's a shame that you don't run into it, because going and doing it of your own volition for your own fun now would be a little bit much. But if someone made you do it like in grade 12, it would actually be a good thing. As I said the other day, my friend Dan used to say, it just makes you a better person. It's cool. It's really cool math once you understand it. And the fact that there is a mathematical function that just says, oh yeah, we can find the area under a curve. There's a way to do it. It's pretty cool. Also, it was discovered by Isaac Newton. So, that's cool. But you might be saying, most of you are saying, I don't know calculus. There's a couple you know it, but you're saying, I don't want to do integrals, which is fair. Well, that's too bad. It's too bad that you don't know how to do calculus. It's too bad that you got bad advice from your high school guidance counselor. How many math courses are available in Ontario in high school? At the final year? in grade 12?
It's gotta be at least 4.
There's 4 different ones? Okay. Yeah, we had 3 in grade 13, and then 1 in grade 12. Okay. We had algebra, functions and relations, and calculus. And I took calculus in grade 12. I still have that book. It's a good book. It's a good textbook. Anyway, let's look at the normal distribution. That's the function. So y equals or f(x) equals that. Again, I'm never going to ask you this. I'm just trying to show you that there really is there's an equation of that line, of that curve, okay? The couple of you in here who know some calculus know that that would be a real bitch of an integral to take. It would be evil to take that integral. So you just take the integral of this function, blah, blah, blah. So let's say you want to know how many people have an IQ between, what did I say, 95 and 107? Yeah. You just take that integral and put in 95 and 107. It's easy. Oh. Easy. Okay. So you can take a look at this and you can see that all the statistical terms in this equation, right? 1 over the standard deviation times the square root of 2 pi times e. You know what e is? It's a constant. It is the base of the natural logarithm. It's roughly 2.71828. It's one of those constants that are, it's like pi. Like there's just certain weird things about our universe that keeps showing up. We're going to give that a name. So that's all e is. It's just another one of those weird constants like pi. And that's raised to the power of negative x minus the mean divided by 2 times the variance. So you'll see a lot of terms in there that, you know, variance and mean, standard deviation. There's a lot of things in there. It'd be nice if we get rid of them, make it a little bit easier. Well, actually, that's what we end up doing. So if we made the mean 0 and the standard deviation 1, all the things that have mu are going to come to 0, and all the things that have sigma or sigma squared are going to be 1. It's going to make life a little bit easier. In fact, that function is not a fun one to take an integral of either, but it's easier. So now this is really simplified. All the sigmas and the mu's are gone because we've replaced them with a 0 and a 1. Okay, that's great. So in fact, we call a normal distribution with a mean of 0 and a variance of 1 a standard normal distribution, or a Z distribution, right? Questions so far? Okay. So if our original question was how many people have, or what's the probability of getting rather, an IQ, finding something that IQ, was it 95 and 107, what we can do is convert everything to a Z-score and then look up probabilities in a table. So that's what I did here. It's not trivially easy. So I'm going to 100, and from 95, I found out that what the 2 Z-scores were, and then I looked up the probability of those 2 Z-scores in a Z table. Okay. That's all I did. Nothing fancy. Stuff you know how to do. Stuff you have done in the past. So this is why we standardize things and make them have it be a normal distribution with a mean of 0 and 1. It's because it allows us to look things up in a table. We don't have tables with a mean of 100 and a standard deviation of 15, because that's what IQ is. We don't have tables with a mean of whatever and a standard deviation of whatever. We do, however, have a series of tables with a mean of 0 and a standard deviation of 1. So if we turn everything into one with a mean of 0 and a standard deviation of 1, we can then look things up in a table and easily find these probabilities. Because some poor bastard did calculus for you about 150 years ago. Somebody was sitting there working out all the numbers on that table. some almost certainly poorly paid graduate student was writing these things down, writing them down, and that's why we know this now. You should, now whenever you do anything with statistics, you should just think back to the people 150 years ago that used to did all of this from first principles and did all the calculus for you. You should be thankful they existed, because you'd be doing it in an entirely different way if they weren't. You'd be doing all the calculus every time. So this is why we turn it into a standard deviation, a standard normal distribution with a mean of 0 and 1. I'm not going to show you how to look things up in a Z table. Go back to your notes and look that up from 2026. I actually did that with my calculator. My calculator has a Z function built into it, so it'll tell me probabilities of Zs. Easy enough. This isn't something you're going to have to probably do very often in this class. You've shown us you can do word problems. It's the kind of thing might show up on a test. You know, how would you do this? How do you tell these are different? Or whatever, something like that, sure. All right. So mean of 0, standard deviation of 1 allows us to use these standard techniques. So as I said, somebody did the calculus for you. So you just look things up in a Z table. All right, sorry, I mistakenly clicked the link. There we go. Okay, so what if you take a look at this link, and I will, you can play with this. This is actually a way to do this just with a computer and not having to write it all out. It's very straightforward. This guy, David M. Lane, has all kinds of great material out there. So I mistakenly clicked on that link, and that's why the YouTube video went away for a second. But this is what you end up getting. So you see what I've done here is I've actually put the values in between negative 0.32 and positive 0.466 for our two Z scores. You would normally look this up in a table, but we don't need to. We got this nice tool here, and it told me the answer. Like, it just comes out. And this is why you can draw yourself a picture and go, okay, it's between there, and go, okay, that's what I'm looking for. Yes, please.
But we'll have to look at the table, right? We won't have this.
You don't have to. I mean, yeah, it's possible. If you have that, you can use that.
Okay.
Yeah, but you can always look up things on a table too. Sure. This is the output, basically. What I'm telling you is, and we'll look at this right after we're done. I'm done going through this, and you can see that it will come out exactly the same. It's a really nice tool. It's very useful. So you might want to bookmark that. All right, to conclude this, and then we'll talk about some stuff more. So some poor person did calculus for you. I want you every time you think about that to remember them. That's the first thing. Seriously, just think, oh, that poor. Thank you. Because you didn't have to do more advanced math. We just looked stuff up on a table with that handy dandy web tool I showed you, and it's really pretty easy. And this allows us to make statements about probabilistic statements about means and standard deviations without really knowing anything about the parent population, which is kind of cool and scary. Now, I know you knew this. You knew how Z-tests work. I know you knew how to look things up in a table. You knew all that stuff. Now you know why it works, right? I hope you can see that it would be a real pain to show you this in second year. We'd lose 2/3 of you right away. Right? Questions on this? I want you to understand this, so I want to have questions. You have questions. I'll go over some stuff in a second as well. But, all right, so let's finish up this video.